السلام عليكم قوتابیانی خۆشەویست لەوانەیە ڕابردوو باسی electrical current و resistance کرد لەوانەیە ئەوڕۆ باسی سێکشنێکی نوێ دەکەن انشاءالله and that is electrical power. یەکەم شتکەوە هەیتمان it is the sources and types of electrical current. من پشتری باسی ئەومان کە گوتمان the potential difference is basically driving the electrons through the circuit. هەر کاتێکە potential difference مان هەبوو دەتوانی push بە ئەلکترۆنەکان بکاتن so that they can flow through the circuit. When electrons flow through the circuit gutman over a certain time we have current. When current it is the rate of charge flow babbling basha. When charges flow over a certain time, let's say through a unit area, you can call that one current basha. Gutman basically potential difference provides the energy. When the batteries and generators supply energy that then by electron can and by charge can so that they can flow through the circuit. Without them, of course, electrons and charges cannot flow through the circuit. And batteries provide energy to the charges so that they can flow through the circuit. The twin billion batteries maintain a potential difference across the terminals by converting chemical energy into what? Into electrical potential energy. The twin billion can convert and chemical energy convert the electrical energy. What the twin billion patriakanish they continue to supply electrical energy to the charge carriers until there is no energy left, and until chemical energy is depleted. يعني هذا بالنسبة لنا أو كاتي مثلا you have to replace the battery with a new one. That can also provide energy to the chargers, and that is generators. We can say generators like this one here. This is a generator, right? So generators generate electrical energy. These electrical energy Babylon provides the energy to the chargers so that they can flow through the circuit. When it comes to generators, we have two types of generators which we are going to study in grade 12 inshallah. We have basically DC generators and AC generators, Basha. But first of all, let's talk about the types of current that we have. Basha, one of them is Gutmano Zorani and Bablano Taipani Karentika. We have the first one, we have something called alternating current, Basha, which is basically for short, it is called AC Oidikashan. It is direct current, for short, we call them DC. Now, actually, Kashmani, you can add them, Basha, which is in grade 12, is going to be pulsating DC, Basha. Pulsating DC, Basha. What is the difference between alternating current and AC like direct? These are the two main ones here. You can say alternating current, it alters, it changes periodically, Basha, reverses direction. You can see here, for example, if you have a wave in here, you can see that these are, Basha, it becomes positive and negative. When we have the positive side and the negative side. Magnetic صفر beaten at this point is maximum positive do add the beta صفر the beta maximum negative do back to zero. When this side is positive, this side is negative. Both the magnitude and the direction is changing as well. But later you can see that only you can see that the even the magnitude actually is not changing here. That is called direct because it is almost like a direct or straight line that it doesn't change. That would be for alternating current. That is what it's called, by the way. And this is the symbol of alternating current AC. It's like a sine wave here and a wave here. And this would be the what is it called? The graph, the diagram for DC. And of course, DCs comes from, we can say, batteries, Basha. Batteries would be one of them that provides that. Alternates periodically, both magnitude and direction change. Later follows bubbling and the flows in a single constant direction here. Basha later no direction, no magnitude, assuming that this is from a battery. What about pulsating DC? This is going to be in grade 12 inshallah. Only the magnitude is changing. Basha. The direction is not changing because we only have the positive side, but because its value increases and decreases, only the magnitude is changing, but not the direction. It is going to be pulsating DC, which is going to be for grade 12. Because it is, like changing direction here, it has frequency. Frequency, this up and down here, you can call this one frequency. How many times does it go up and down in 1 second? That is going to be frequency. We'll study this one in grade 12 again, inshallah. But this one here, it has zero frequency, because it has no up and downs here. So it is constant right here. This is generated by alternators, like a coil, for example, or power plants like the generator that you see. It could be any other power plants, let's say. But this one, you can see that it's generated by batteries. It could be solar cells, or even we can say DC generators. But by the way, this would be directly from a DC generator. But of course, this can be smoothed and changed into something like this one here. But this one here can be generated from a DC generator. باشا سيدي كشمان هي وانا ديكا توان بلا نو خالن ديكا زيادة بلا ما قربيان زاني خراب نية. This is efficient over long distances باشا with minimal losses. كاتا قربتي كارباي كل لشنك يدور بقازيوا. You'll have to use this one because power loss كي كمان توان بلا كم تريني بخسار دتي بس ليرة قلت مان inefficient for long distances. It is not good to send this one from one city to another because the power loss is going to be a lot. This is used because عندك زيازي كهربائية device man here that can only work with AC عندك شدي كشماني that can work only with DC. For example, let's say heater, oven, boiler. These are things that can, let's say your refrigerator. These are things that can work with AC, alternating current. But electronic devices, all of them, because they're fragile, they need a stable, let's say, voltage and current there. So they need to have or DC current, otherwise it might be damaged here. شتش دي كش معناه بابا كاتت وان electrical يعني energy transfer energy transfer شتك معناه بابا and that is power باشا. But before that we know that power ده كاتت سي ليرة باشا power we can say it is equal to work done باشا divided by the time here, or you can say the work done by the charge carrier divided per unit time here. Why this 20 let's say work done able to say energy basha. So if you cross multiply here, we can say the energy that is equal to power times the time here basha. But this power here, right, we have three equations for power. The first equation for power, we can say power it is equal to what? It is equal to current times the voltage here. We mostly like use this one when the power is sent basha. Let's say from one place to another. Of course, it could be used for pure ohmic resistors too here, or devices, basha. Another equation for power, we can say power they got the current square times resistance, basha gargoti power loss like it's and then baby no kati, you can use this one. Another equation for power that can also be used for power loss, you can say dissipated as well. We can say it is equal to the voltage squared and delta V potential difference divided by the resistor here. You could say potential difference delta V or V doesn't matter here, right? At this point, as long as you multiply this correctly, kata, we have three equations that we use them for power, baba. Current times the voltage, current square times the resistance, potential difference squared divided by the resistance. For the equations that we have, we mostly use this equation, Masha. Kata, keep an eye on this one. But next year in grade 12, like we're mostly going to use these two equations. But for now, this is the equation that we're going to use for most of the questions that we have. Basha baba. Nagat lo khalibi kata. Power the we can say power it is equal to the rate of work then basha ha pashtri gutman hash the rate of yani divided by the time, the rate of work then basha kata work done divided by the time, that'll be the power basha. The unity power it's here. Let's not forget this. Then power is measured in watt basha. Is measured in what? Is measured in watts, you could say, and the symbol for power it is W, we can say, basha. Zor basha. Power before we continue, there is one more thing that we have, basha, and that is this one here. This power that we use, by the way, or this energy that we use, it is measured in kilowatt hour. So basically, it doesn't measure, for example, what is it called? How much ampere, let's say, you're using. No, it just measures how much energy you're using. If you look at this one here, this energy, it is measured in what? Obviously, it's measured in joule. But power here, it is measured in what? Is measured in watt. But if we're going to use this power for a month, of course, watt is going to be a huge number. So instead of watt, we're going to use something. You can call that one kilowatt, basha. And then for the time, because we're using that for a month, so kata second is going to be a very big number in seconds. So instead, we're going to use hour instead. So of course, now we have something called kilowatt, basha, kilowatt hour here. So this kilowatt hour, this is the unit for the energy that we're using basha. But once again, if you're going to convert this one to energy, you'll have to convert this one again, good man. Each kilo it is 1,000 watt in here, and then we know that each hour is 3,600. We can say seconds here. So now we can say, according to this, joule that's it. Joule it is equal to, we can say 3. Let's just call this one 3.6 times 10 to the power. That is going to be 6 basha watt second. So we can say that basha. Or let me just write this one here basha. We can say 1 kilowatt hour basha, that is equal to 3.6 times 10 to the power 6 joules of energy basha. So this is something that we have. I believe it is best to know. Kata baba wilira gringa gutman bzana power the kata tse. We'll get back to this one later, basha. Gutman power the kata energy and work done over time, basha. Doesn't matter. Work done per unit time. Later, once you cross multiply energy, the kata tse power times the time. It's gutman later power equation power, and we have 3 equations for power, basha. This equation is used mostly for power cent. All right. Now power the crib kata current times potential difference. The crib kata current squared times the resistance. The crib kata potential squared or change in potential squared divided by the resistance basha. So agar pisara ke dawa power ikad, we'll use one of these equations. Agar energy te dabu drabu yanda akrabu, and then with the power, then we're going to use this equation basha. Gatman power is measured in watts when and energy obviously measured in joules, and time is measured in second basha. Gatman kata power the kata swab equation, okay, it is the rate of yani something divided by the time, the rate of which charge carriers do work. Kata tonibilan work done divided by the time measured in watts. Kata equation gatman power work done divided by delta time here. Power the kata current times potential difference. Whenever we can express the power dissipated here, baba, this dissipated, that means you can say converted. It's mostly used when we say the power is lost to something. We can use that, but officially it means when we say dissipated, that means converted to something else, basha. So whenever it says converted to something else, we can say power the kata current square times resistance, or power the kata potential difference square divided by the resistance. Well, we have almost like the kata it my potential difference the kata current times resistance yan peshtribono ayman danusi tamango r the kata asha r the kata potential difference divided by the current. Whether you write it this way or this, doesn't matter basha. These are the same thing here. You can say kata the power, p is the power measured in watts, which is basically the letters W. Gutman watt the kata joule per second. So عندك equation man here عندك بسعر من هي حاليا كان an electric space heater is connected across this much volt. So this is potential difference, we can say basha, and then it says outlet. The heater dissipates so this much watt, that'll be the power in the form of electromagnetic radiation and heat. Calculate the resistance of what? The resistance of the heater. Equation power, the equation that we use, equation baba, out of the 3 equations that we have, and clearly this one dissipates and it converts the electrical energy into something else. Kata, we can use the one of the 3 equations that we have one, but because later potential difference to power man, which equation do you think it is best to use, baba? Out of the equation that we have, the third one would be the best. Power the kata delta and potential difference square divided by the resistance. When you later matsman the resistance command the kata because subject resistance the kata potential difference square divided by the power. When you potential difference command, it is 220 power command it is 1,320 watts. Once you do the math, of course, you will get 36.7 ohms basha. 36.7 ohms. This would be the resistance of the heater. All right, that is one of the questions that we have. A 1050 watt electric toaster. So this is the power. It might not tell you this is the power directly, but you can always tell by the unit. When you got a 1050 watt, that is the power. Operates on a household circuit, basha, of this much volt. This one does not tell you the potential difference, but you have to recognize this by the unit. What is the resistance of the wire that makes up the heating element of the toaster here? يبقى التونبل power كمان سنة بابا 1050 watts. عشان potential difference كمان بابلين 220 بشارك دلار ريزستانس كمان سندا قلت ما ريزستانس دكاتة دلتا في سكوير لست باور ونيا دلتا في كمان 220 بس او سكوير اللي بير مكا. I don't know if I wrote the other one or not. Let me go back to this one. I think there's no way to get back to this one here, but just in case, I don't know if I did this square or not. All right, so let me just redo this one just in case. R دكاتة قلت من delta v squared over power قاعدة بيتا 220. Don't forget this square here, باشا. Why do I feel like it didn't do it? Square and then divided by 1320. Once you do the math, of course, you'll get 36.7 ohms. That is going to be the resistance of the heater here. Okay. What else do we have? قلت من ليرة لو بساري بابا قلت من power كمان سمبو. The power is 1050 watts باشا. And then voltage and potential difference at 220 volt. What is the resistance of the wire? Resistance كيف بينا؟ زور باش. قلت ما resistance دكاتة man because we have power and potential difference. Resistance دكاتة potential difference squared divided by the power here. ما ليرة 220. I got the square can be divided by the power which is 1050. Once you do the math, of course, you get 46 ohms, and that is going to be the resistance of the toaster. All right, now this question, I believe it's easy enough, says what is potential difference? They need the potential difference here. Calculate, a calculator is rated this much, so this is the power, all right, and then this is the resistor. What battery potential difference is required for the device? That's man power man here, resistance man here, potential difference, okay, but we know, right? So you could do the same equation here. Let's just write what is given here, 0.10 watts. And then resistance, it is 22 ohms. Potential difference okay, delta V okay, bubino. Got the line power دكاتة power دكاتة delta V squared over resistance, right? You can cross multiply now. Okay, so that is what it is. We can say potential difference squared دكاتة power times resistance. But we want potential difference, not the potential difference squared. So take the radical for both sides of the cancel. Then potential difference دكاتة radically power times the resistance here. Got later power command senda. It is 0.10 times resistance command 22 ohm. Once you do the math, of course, you will get 1.5 volt, and that is going to be the potential difference that is required to be connected to the calculator. And that's, I believe, easy things, right? Come on here, but this question obviously it is two parts. Says an electrical heater operated by potential difference delta V man here across the wire of a, let's say, wire of a total resistance R man here. The first part of a question says find the current. When you got a delta V R man here, baba, how do you find the current? By using Ohm's law. When you got the 20 blind, let's write what is given here. Delta V, it is 50.0 volt. Resistance command, it is 8.00 ohm. Basha. Find the current. Part in the first part of it. Using Ohm's law, delta V over current. When you do a swap, delta V over R, delta V كمان سنة. It is 50 volt divided by 8, and then we can say the current, it is equal to what? It is equal to 6.25. You could say 6.3. That is totally fine. That is going to be ampere. That is the first part of a question. The second part says, and the power rating of this heater. Now, of course, for this part, you could use different equations. Because we have the resistance, we have the current, we have the voltage. Now, you could choose whichever the equation that you want to. So let's say power دكاتة, we can say delta V squared over the resistance. V كمان سنة, it is 50, but I got leave it man squared divided by the resistance, which is 8. Once you do the math, of course, you'll get 313 watts. This is the power rating for, we can say, this electric heater. All right. Electric companies measure energy consumed in kilowatt. These electrical companies, like they don't measure how much current or how much power it is delivered, how much energy is delivered to the house. They measure how much energy is used, let's say, by this household, right? So how do they do that? 1 kilowatt, this is how they do that, Basha. Power companies charge for the energy, not the power, Basha. They charge how much energy is used, not how much power is provided to the house. Let's say the unit of energy used by electric companies to calculate, the consumption, which is basically kilowatt hour, is defined in terms of what? Of power. So we can say 1 kilowatt hour is the energy delivered in 1 hour at a constant rate of 1, we can say, kilowatts in here. Kata 1 kilowatt the kata san baba. Kilo stands for 1,000 watts, basha. The 1 kilowatt stands for 1,000 watt, basha. So that is one of it, basha. That is one of it. And of course, if you want to divide this one, let's say, or convert this one to joule per second, you could simply, or joule, which is the energy, you could do that easily, basha. And we know that every hour it is equal to 60 seconds. Without doing this one, Baba, we can say 1 kilowatt hour here. Gutman, 1 kilo, every kilo is 1,000. Times 1,000. Every hour it is, that is going to be watt. And then every hour it is 3,600 seconds here. We can say, how much is this one here? We can say 3.6, Basha, times 10 to the power 6 watt second on the kata 3.6 times 10 to the power 6 joules, basha. Kata, because watt second, obviously it is equal to joule. This is how much we can say energy used when it comes to kilowatt hour. We can say 1 kilowatt hour, basha, it is equal to 3.6 times 10 to the power 6 joules, basha. So the electric company does not charge for how much power is delivered to the house. It charges how much energy it is used, basha. And of course, they try to send the power at a high potential difference that the energy loss can be to. Now, section review of 7.4, we can say, what does the power rating on a light bulb describe? Whenever you have an electrical device, obviously, once you look at it, there is, for example, is written 10 watt, 20 watt, 100 watts, 200 watt. What does exactly this means here on a bulb? We can say the power rating on a bulb, Bablin, and on that device, it tells you and describes how much energy uses per watt per second. Yan Bablin, how much energy uses per watt per second. That is going to be measured in watt, basha. Kata namago power the kata energy per unit time. So when it says this much watt, yani this much energy every second, basha. Second question says, if the resistance of a light bulb is increased, how will the electrical energy used by the light bulb over the same time or same time period will change? Of course, if the resistance increase, kata tsile de baba, the twanimblin au power ka bakardetin, basha, yani energy ka bakardi, it becomes less. Laberte, of course, we can say the electrical energy used by the light bulb will decrease. Energy the power times what? Power times the time. What is the relation of power and resistance here? Of course, we know that if the voltage is what is it called? If the voltage is constant, we can say power the delta V squared over resistance times delta T. The energy, of course, it is going to be less if this is constant, because we can, based on this, we can say the energy and resistance are inversely proportional. Question 3 says the potential difference across a resting neuron in a human body is about 70 millivolt, and the current in it is approximately 200 microampere. How much power does the neuron releases? So you have the current, you have the voltage. All you have to do is just multiply the two together. So we can say power the current times the voltage. Micro, it means 10 to the power negative 6. Masha. Let's just write this times 10 to the power negative 6. Millia is 10 to the power negative 3. Now you just multiply the two, you get the power in watts, and that's it. So these are easy stuff, I believe. Now a few questions here, real quick. Says the end of chapter 7, we could say review, and it says if a point charge is displaced perpendicular to uniform electric field, which of the following expression is likely to be equal to the change in electrical potential energy here? You do remember previously we said, Gutman, these are the electrical field when you, okay? So these are uniform electric field. Gutman again, if a positive charge moves in the direction of electric field, it loses energy. But if it is negative, all right, it is going to gain energy, whether if it is moving in the same direction when you. So let me just walk you through all of it now. If it is Gutman, a positive charge, if it is flowing in the direction of electric field, it is going to lose energy. if it is a positive charge. But if it is moving opposite to the direction of the electric field, it gains energy. It gains energy. But if it is an electron here, right? If it is moving in the direction of an electric field, that is going to gain energy. If it is an electron, if it is moving opposite to the direction of electric field, so this direction of electric field, it is going to lose energy. But that's not the question here. The question says if a charge moves perpendicular to a magnetic field, for example, whether positive or negative, if it is moving perpendicular, up or down, doesn't matter. As long as the angle between the direction of electric field and the motion of the charge is perpendicular, will there be any change in the electrical potential energy of the particle? The answer is no, so we can say the change is going to be 0. That would be the correct answer here. Another question here says, what happens to the charge on a parallel plate of a capacitor if the potential difference is doubled? We can say the charges on the plates will also be doubled. The charge and bubble C the says C the Q over delta V here. What is the relation between the two here? You could do this one here. So we can say delta V the Q over C. Now you could see the relation between delta V and Q. It is directly proportional, right? So now in this case, of course, if you say, or you can even make Q the subject here. Q the we can say delta V times C. If this is doubled, of course, now the charge on the plates will be doubled too. All right, now there's this question here. I believe this one is easy. This is the voltage. This is pico. I got 10 to the power negative 12. What is the charge on the capacitor? You could do this or solve this question yourself too. What is the direction of the conventional current in each case shown below? Direction current, because the current flows in the same direction as a positive charge. The direction current is also the same direction as a positive charge in here. What about if we have negative charges? The direction of the current, it is going to be what? It's going to be in opposite direction to this one. In A, we can say the same as positive charges. Direction current is same as positive charges. For part B, we can say it is opposite. Direction current opposite, we can say opposite to the direction, opposite to the, let's just say to the negative charges. To negative charges. And that's it. Opposite to the negative charges here. Good manera, same, dirish, opposite. What factors affect the resistance of a conductor? There are 4 factors. That is clearly the length, the cross-sectional area, the type of the material, and the temperature. All right, the 20 blend 1, 2, 3, and 4 as well. The length, which is directly proportional, cross-sectional area, which is inversely proportional, and then the third one, type material, okay. And then number 4, temperature. These are the 4 factors that affect the resistance of a conductor. Each of the wires shown below is made of a copper, assuming that each piece of wire is at the same temperature, which has the greatest resistance. Which one of them has greatest resistance? What am I saying? Resistance resistivity times the length divided by the cross-sectional area. Of course, this to have the same length. Resistance and area are inversely proportional. We need the greatest resistance. Between these two, which one of them do you think has more resistance? Of course, is going to be this one here. The resistance of this one, beyond bubble in C, has the greatest resistance. Greatest R, it is going to be what? It is going to be C. Because thickness. What about the second part? Says which one has the least resistance? resistance كم بدرجة كوبي بابا. resistance كم ترى وهتا area كشي جوتري بيتن resistance كم ترتبي كاتا أو دومان هي عين دريجيان هي and bubbling same length كوانيا بس استا we have one of them is thick the other one is thin kata. Which one of them has less resistance? Of course the thicker one here kata. Part A we can say has the least resistance. Basha? Least resistance, that is going to be what? Is going to be wire A. Again, these are all the same type of the material. Now chapter baba. These are some standardized proportion عندك percentage وين كده محالب كsolve يعني كل خد باشا. And then I believe you could do them, and these are the answer keys if you want to double check or just check your answers, Basha. And I hope you could do them. Basha, now let's talk about chapter 8, which is about currents and electric bubbling circuits and electric elements, Basha. Now, what are we going to learn in this chapter, Baba? We're going to learn about schematic diagram on circuits, bubbling. How do we draw diagrams, resistors and series and parallel, complex resistor combination. The first thing we can say schematic diagram diagrams and circuit like how can we for example, once we have a light bulb, how do you represent light bulb so that everybody, whenever they look at a circuit, they know that this thing is a light bulb connected to a circuit. The first thing the schematic diagram whereas the representation representation of a circuit that uses lines to represent wires and of course different symbols to represent component. او بابلن diagram تمام بشان داتن بابا هالكاري سركت كمان بشان داتن ك line بكاردي بشان داني واركان وهروها بابلن different other parts and symbols symbol ديكي جواز for other let's say different component باشا. For example استاو diagram مان هي نتوان بلن سركت مان هي ليرا باتري مان هي ليرا رستر مان هي ليرا light bulb مان هي ليرا switch مان هي اوش واركا دي بينن ونيا. How do we, like for example, draw a diagram for this? It is not easy, Baba, because it is time consuming, and of course we're not an artist, by the way, so we are not able to draw something like this always. Kata will draw a simplified and easy diagram, Basha, to represent this, which obviously represents the reality, we could say. Kata, for batteries, Baba, if it is more than one, this is the symbol that we use, Basha. For battery, you do know that, for example, if it is a single battery, we draw two lines, Basha. One of them is longer, at a short and thick, you could say, Basha. So kata, the longer one represents the battery, the positive side, the short and thick one represents the negative side. That is if it is one single cell, Basha. But if it is more than one, we call that a battery, and then after that, we're going to draw more and more, as you could see here, Basha. So these are obviously batteries connected positive to negative, let's say. So one terminal, one side is going to be positive, the other side is going to be negative, and this is how we connect that. For wires, this is what we're going to use, just straight wires here, I could say. For resistor, we're going to use this symbol here, which you can see that it is almost like up and down here, which makes it's almost like something very difficult for electrons to move back, let's say up and down here, instead of moving straight, so which slows the current down, limits the current down. Symbol for a light bulb, Baba, we could use this one here. There are many the symbols that we could use for light bulb, but these two, the most common ones, this is one of them, Basha. And then another one that we use, sometimes we use a circle with a cross in it that is also can be used as a symbol for battery. What about for a switch, Kaka? We can use this one as a symbol for a switch, Basha. So these are the things that we use. Now, that is what is called schematic diagram and bubbling, what is it called? Schematic diagram for electrical circuit. When we have a wire conductor, we use lines here, Basha. So this represents a wire that connect elements with conductors. You know that one, yeah. Resistors or circuit load, Baba. Resistor, يعني circuit load كان bubbling أو component أو device Basha. We can draw them this way, Basha. So you can see that here, a bulb or a lamp, Gutman, you could use this one here, or you could use this one. These makes no difference here, Basha. So these are all devices and bubbling symbols for current. This is the one that we use in this book the most here, Basha. And then if it is a plug, Basha, bubbling This is how it looks like, Basha. And then if it is a cell, Gutman, these are different types of batteries. But if it is a single one, you can call them a cell, Basha. If it is multiple one, you can call them a battery. But nowadays, whether if it is one or multiple, we just call them a battery for simplicity. If it is a switch, we have open switch, by the way. You can see that these two are not connected. These are connected. So this is open switch, this is closed switch, and this is how we draw them in diagram. Okay, and this is a capacitor. You've already learned about capacitors, which are made of two plates, but this is how we draw them in diagrams. Or some of the times could be like this one too here. So that is pretty simple regarding this one. I believe knowing this many circuits and component here, that will be enough for circuit diagrams. Baba, I don't electrical circuit later. Electrical circuit instead of electrical component connected such that obviously they provide one or more, let's say, complete path for the movement of charges. Basha Gutman Katika circuitakan yan bablin wire component can hum complete bunokati, then current can flow to them or flow through the circuit. As the kriya masalan now circuitaka yak path man habitan or the kriya path yan bablin le زيادة لباثك man habitan, which is going to be the next section, which we're going to call them parallel or series circuit. Basha كاتا مثلا دكري بونوعي بيامبستينو where we have one path. Basha دكري مثلا بونوعش بيامبستينو where we have more than one path. Basha, this is basically a circuit, or we can say electrical circuit. This is a battery. This is how we're going to draw the symbol of a battery. Positive like negative. These are the symbol of electrical current. Diagram you could just, for example, draw something like this one here, and then just, for example, at this point, you could draw something like this. These are, of course, different methods of drawing this. Yak path, Basha. What do you mean by yak path, Babalira? There's one way for electrical current to flow, Basha. But then here, there is more than one way. This is what I mean by one path or more than one path. The more than one path. But later, there's only one path for the current to flow. Basha kata key component mane baba. Every simple electrical simple circuit must have four things at least. Man the battery HB, a power supply. Basha the be the wiry PO beaten, the be switch a PO be legal, at least a light bulb so that we can see if it is working or not. Kata we can say that components and simple components of a simple circuit battery to provide a potential difference of voltage or drive the current. Gutman wire man here to connect to conduct the current so that the current can flow through the circuit. Well, we must have a bulb or a load that converts electrical energy into light and heat, and we need a switch so we can control the flow of the current by opening or closing the circuit. Basha? Closed versus open circuit, Baba. What do you mean by closed circuit? When we say closed circuit, yani the current can flow through the circuit. Basha, it's closed, complete, Basha. If it is open, as you can see here, the current cannot flow through the circuit, so the circuit will not work. Okay? No dukhale bitan. What else do we have? Short circuit can be hazards, Baba. What do you mean by short circuits? Yani, when positive, Babylon, when electrical current is connected, if you connect the two ends of a battery, of course, this is not safe. I'm a shorty pedaling, Baba, because you can see sparks, of course, will be ignited, and of course this is not safe. And you've seen that like every year there are a lot of damages, and God forbid bad things happen because of electrical circuit. You must make sure that for example, you use proper wires, proper settings. Sources of potential difference on electrical energies, the circuit's EMF. Basha Kutman, Baba chip provide the energy so that electron and charge can flow through the circuit. Basha. Power supply. So without a battery or power supply, current cannot flow through the circuit. Got a potential difference. It provides energy to the charge carriers to be taken to the device, to the resistor, to the load. Light bulb chip provide the energy light bulb energy. Of course, who's providing energy for the light bulb to work? Of course, it is the battery. We can say the battery provides the potential yan bablan the energy basha. The battery acts as a we can say charge pump, supplying energy to move the charges through the circuit. I get maybe no battery means no current, no current means no light. And of course we can use Ohm's law for that as well. For conventional current, good man, the terminal voltage is less than the EMF. What do I mean by this one? عادة positive side and negative side man هي قاعد لوي بيتن ويكشد كشمان هي inside a battery, good man, there is a small resistance. Good man, simply good man, this symbol stands for this symbol is for the resistance here, and every battery has a resistance in it. But this is the reason why of course you'll see that, like on its own, of course, good man, the voltage of course is going to decrease more and more because that resistance inside the battery makes it lose energy and bubbling over time, whether it is because of the chemical reaction and it makes the battery get hot. So this would be some other you could say problems that we have with the battery. For simplicity's sake, in problem solving, of course, is going to be assumed that the internal resistance is insignificant. Just for simplicity. Potential difference across a load equals the terminal voltage. But in a circuit, the battery converts chemical energy to electrical potential energy, and electrical energy or the energy will be converted and will be sent to the device. So whether if it is a light bulb or could be anything else. But light bulb be once connected the same voltage will be on the light bulb as well. This is what we mean by what is it here? Good man, the potential difference across the load equals the terminal voltage. Yani bablin o patriaka voltage hertz and the baba. Lesser bablin terminally to end the bablin o load and o device man, it is going to be the same amount of voltage over them. But for this case, of course, we can say the switch must be closed for this torque. Now, so in a circuit, good man, the battery converts chemical energy to electrical potential energy, which then transforms into other forms, which is light and heat, by the load, you could say. Good man, section review man but they'll identify the types of elements in a schematic diagram illustrated in figure 4 on the number of each type, you can say. So what are the things that we have here? Here we have a battery, or you can say a cell baba, or battery, we could say. These are, of course, you can call these light bulb. And then what about this one here? Can we call this one a switch? And of course, it says number them. We have 2 light bulbs, we have 3 and then Gutman Celica, it is, or battery, we have 1. Of course, you don't have to count them because these are just connecting wires here. Switch, there is 1 switch. What about the number of loops here, Baba? That is 1, this is 2, and this is 3 loops as well, if you want to consider that as well. These are all the things that we have. Using the symbol listed in table A, draw a schematic diagram for a working circuit that contains 2 resistors, an EMF source, and a closed switch. Now, how do we answer this question, Baba? Man, let's a working circuit that contains 2 resistors, Basha. So here's 1 resistor. This is 2 resistors. So this is 1R, this is 2R. You can call R1 and R2. An EMF source. EMF source again. Who's providing the EMF source, Baba? The battery, we could say. And then there is a closed switch as well. So you can consider a closed switch as well. And this is a switch, Basha. So this is one diagram for that. It doesn't mention use 1 path or 2 paths, so it is up to you whether you write it this way or the other way. Question 3 says, in which of the circuits pictured below will there be no current, Baba? Current can flow here. What about this one here? You can see that the circuit is open, no current can flow. So this would be one of them, Basha. So current in this one does not flow, Basha. What about this one can flow because the circuit is closed and there is a battery and everything. But later it's not connected, current cannot flow in this too as well. We can say figure 6 and 8 no current will flow in them. Basha, got that? We can say no current flow in figure Gutman 6 and 8. Basha, these two, the current will flow, so there's no problem with that. All right, now what about question 4 says if the potential difference across the bulb in a certain flashlight is 3 volt and the potential difference across the combination of battery used to power it, Basha. Potential difference across the combination of batteries used, Basha. So if the potential difference across the bulb in a certain flashlight is 3 volt, what is the potential difference? So potential difference that is the same potential difference that is going to be on the battery on the loads in here. I get a potential difference load to terminal if it is 3 volt and the potential difference is set Patrick it's and that is also must be 3 volt as well, and that is as easy as that. So this one has to be 3 volt, Basha, and that's it. 5 for Jan Bubbling. The last question here says, in what form is the electrical energy that is dissipated to a string of decorative light bubbling lights dissipated? Dissipated means what form is converted into. If we have a light bulb, right? So we can say the energy will be converted to what? Will be converted to light, all right, and heat. Light is going to be the useful form, Basha. Useful output, we could say. But then heat is going to be the wasted one, Basha. Wasted. Got the electrical energy converted to light and heat. The light is the useful form because it is decorative light, Basha. Dikash is going to be wasted, Basha. Inshallah, next time we'll talk about resistors in series and parallel, Basha. That'll be the end of this lesson. Till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.